Hi there, welcome back to the channel, and today I'll be introducing to you the energy band diagram, which is used in the semiconductor theory. So I will be showing you where the energy band diagram comes from and what an energy band diagram can tell us in terms of the behavior and the properties of the material. Is it N or P type doped? And I'll be also going over the parameters such as Fermi level, intrinsic level. Okay, so for example, let's look at one atom of silicon, which has 4 electrons in the valence shell. So if we look at the energy levels here, they have discrete energy levels of a single atom, yeah? 1s, 2s, 2p, 3s, 3p, and this is the conduction level. These are discrete. So let's say we have a pair of atoms. Oops. They will share the electrons like this, and they will still have the electrons like that. So if we have a pair, what happens to these discrete levels is that they actually become two levels. So depending on the number of atoms, that also influences the number of discrete levels of energy levels, like this, yeah? So based on that, we can make the assumption that the higher the number of atoms, the more discrete energy levels there are, and that number can become very large. So let's say we have 10 to the power of 18 atoms per cubic centimeter. So that's a number of electrons so dense that we get what what is called, uh, energy bands. So in terms of energy band diagram, what we're really interested in is the conduction band and the valence band. So in between these bands, we have what's called the forbidden gap. So there are no available discrete energy levels, no available electron states in between the conduction and the valence band. However, if we have electrons in the valence band, with the right amount of energy that can travel through the forbidden gap to the conduction band. Okay, so in terms of material, there are three main scenarios in terms of energy band diagram. So let's look at scenario one. We have insulator. Oops. Okay, so for example, let's look at silicon oxide. The band gap for this one, very large. It's about 8 electron volts. So in terms of the electrons, it's quite difficult then to reach the conduction band, almost impossible, which makes it poor for conduction. Here we have semiconductor, of course. Let's use silicon as an example. Um, so the band gap is not as large as insulator. So what that means is that various forms of energy can give the electron enough energy to reach the conduction band. Can be light or heat, for example. You know, there's more than that. And last we have metal. So actually, metal doesn't have band gap. They they actually overlap. Oops, that's not EC, that's EV, but just for your information, there we go. So as this happens, minimum energy is required to reach the conduction band for the electron, which makes it a good conductor. Okay, the next parameter here we have is Fermi level, typically noted as EF, like this. Okay, so let's say we have intrinsic semiconductor, so it hasn't been doped with any impurity. We can then assume that the Fermi level will be roughly in the middle. It's like a probability of where electron will be. So because this semiconductor is intrinsic, is not doped, we can assume that electrons will be here. And if we have N-type semiconductor, it's been doped with N-type material. I'll explain this later. EC, EV. So in an N-type, we have more electrons. So we can then assume that electrons, they're more likely to be in the conduction band because more electrons, more chance of electron jumping from valence to conduction band. And the opposite is true for a p-type semiconductor. If it's been doped with a p-type impurity, that means there will be a large number of holes. And we can then assume that the Fermi level will be down here. Because electrons are less likely to have passed into the conduction band because they're the minority carrier compared to the majority carrier in the p-type material, which is the holes. Okay, you can feel free to pause the video here and take a closer look. These are just all the necessary equations to calculate the necessary parameters that you may be asked to do. So if you have, for example, Fermi energy, intrinsic energy, and the intrinsic concentration, Ni, you can calculate then the concentration of P and the concentration of N. But what is Ni? So Ni is the intrinsic concentration, and if we multiply here equation 3 and equation 4, we get what is called here in the top. This is called mass action law, and it's just a rule basically that Pn equals Ni squared. So if we know Ni and we know P or N, we can rearrange then for the unknown variable. What else? You also need to know what is Nc in the top left. That is the density of states in the conduction band. And a bit further down here is Nv. This is density of states for the valence band. And one more thing I don't think I've covered yet is the intrinsic energy level. So if I draw another band diagram here in the top right, this is EC, EV. So always in the middle is the intrinsic energy level. So here's EI is also equal to EG, the band gap, over 2. And here is the band gap for your convenience. And yes, over here in the bottom we have K, the Boltzmann constant, and T is temperature in Kelvin. And this product always shows up in many of these equations, almost all of them. But over here is where you need to pay attention, because we need to stay consistent with the units. And to do this, we divide by the charge of an electron, which is 1.6 times 10 to the power of 19 coulombs, which gives us then the products kT in this time the unit of electron volts. And this is what we will use to work with the problems. Always stay consistent with the units. That goes for everything. Okay, here's a question for you to try. Given that intrinsic concentration is 1.3 times 10 to the power of 10 per cubic centimeter, energy bandgap is at 1.12 electron volts, Fermi energy is at 0.88 electron volts, find electron concentration, hole concentration, and sketch the energy band diagram. You can assume for this question that Boltzmann constant K is at 1.38 times 10 to the power of minus 23 joules per Kelvin. Let me write that there. And the temperature is 300 Kelvin. So pause the video and have a go. Okay, so let's start by finding the electron concentration. So as you may recall, N is equal to Ni times e to the power of Ef minus Ei divided by kT. So let's plug the numbers in here. 1.3 times 10 to the power of 10 per cubic centimeter multiplied by e to the power of Ef minus Ei. So Ei is half the band gap, so that's 0.56 electron volts, which will consequently give us 0.32 electron volts here in the equation. And remember, we stay consistent with the units. So we have here the kT product. We convert to electron volts, and that will give us 0.25875 electron volts. If you notice here, electron volts will cancel out, and that will leave us with the answer of 4.47. Oops, let's make that a bit clear. Times 10 to the power of 10 per cubic centimeter. That's the electron concentration. Now hole concentration is same thing but with a reversal of sign in the exponential. For your memory and benefit, I'll just write that here. So let's try this one. 1.3 times 10 to the power of 10 times minus, e to the power of minus 0.32 over 0.025875. And that will give us an answer of 3.77 times 10 to the power of 9 times 10 to the power of 9 per cubic centimeter. Okay, so we found the concentrations. Now we sketch the energy band diagram. But before that, I just want to remind you of kT, the kT product. So we have kT here, and the unit is joules, but oh no, wait. Yeah, we divide it by actually uh we divide it here by the charge of an electron. Yes. So that is, we approximate that to 1.6 times 10 to the power of 9 minus 19. That will give us 0.025875 electron volts, because that is electron volts is equivalent to joules per coulomb. Yes, that's the units there. That all checks out. So now let's finish this by sketching the energy band diagram, which we'll do here. So this is EC, EV, here's EI, 0.56 electron volts. Fermi energy is roughly here. What's important is that we write the number here, 0.88 electron volts. and band gap 1.12 electron volts. And that's question solved. Okay, that's all I have for today's video. I hope you enjoyed and learned something new about the semiconductor theory. Thank you for watching.